Hello everyone. Today we are going to learn synthesis of hydrogel and nanogel. In today's lecture, we are going to learn what is hydrogel, how to synthesize and characterize hydrogel, and we are also going to learn nanogels and their method of preparation. At the end of this lecture, we will be learning how to synthesize hydrogel and nanogel through practical demonstration. Let us see what is hydrogel. Hydrogels are three-dimensional cross-linked polymeric network capable of observing and retaining significant amount of water or biological fluid. So due to their unique ability to swell without dissolving makes them ideal for a variety of applications ranging from biomedical to industrial uses. Hydrogel was first reported in 1960 for contact lens application. Let us see the properties of hydrogels. Hydrogels have very good swelling capacity. It has the ability to absorb and retain water, and it is a biocompatible material. It won't induce any immune response. So that is one of the important property for medical application. It is compatible to the biological system. It won't induce any adverse effects inside the body. So that's why it is highly biocompatible. And it also has a very good mechanical property, and this mechanical property can be adjusted from soft to tough, depends on your final application, and the degradation property also can be changed with respect to the final application. The last one is the permeability. We can also control over the diffusion of oxygen, nutrients and drugs. For example, these hydrogels are porous in nature, so it will allow the oxygen, nutrients and drugs to enter and pass through that. So it is one of the important property for various biomedical application. Let us see the factors involved in fabrication of hydrogels. The first one is polymer type. It can be a natural or synthetic polymer, depends on your final application. We have to select the polymer. If you want to go for biodegradable scaffold, we can go for natural polymer, and if you want to have a more mechanical strength, it has to stay for a long time, we can go for a synthetic polymer. And next one is this cross linking density. If you have a high cross linking, it will increase the strength, but it will decrease the flexibility and swelling. The next one is pH and temperature. So the pH and temperature affects the gelation and stability mainly for the sensitive polymers, and the water content influences swelling and mechanical properties as well as the drug release rates. The final one is the concentration of polymer. It will affect the viscosity and network formation during the gelation. So we have to optimize all these parameters, and we have to understand all these factors before we fabricate our hydrogel. Let us see how we can classify these hydrogels. Hydrogels can be classified based on the origin as natural and synthetic, and based on cross-linking also we can classify into chemical based cross-linking and physical cross-linking. And third one is degradability. So it can be a biodegradable or it can be a non-biodegradable. So based on that also we can classify. And the last one is the porosity. It can be a non-porous or microporous or mesoporous or macroporous. So based on the porosity of hydrogel also we can classify these hydrogels. Let us see some of the examples of classification based on polymer type. So based on natural polymers, we can classify as a natural hydrogels. Some of the examples are alginate, chitosan and gelatin. And under the synthetic hydrogel, PEG, that is polyethylene glycol, PVA, that is polyvinyl alcohol, and polyacrylamide. These are some of the examples of synthetic hydrogel polymer. Let us see how we can classify hydrogel based on cross-linking. The first one is chemical cross-linking. Here the hydrogels will be cross-linked through the chemical reaction, and here the polymer chains are connected by covalent bonds. Examples are ester bonds, amide bonds or disulfide bonds. Some of the common reactions include free radical polymerization, condensation reaction and click chemistry. Example is azide alkyne reactions. Here this monomer will be cross-linked using the cross-linker, and it will be a chemically cross-linked hydrogel network. In this way we can make the hydrogel, the porous hydrogel, based on the chemical cross-linking. Let us see some of the examples. The first one is gelatin, which can be cross-linked using glutaraldehyde, and next one is polyacrylamide gel, which can be cross-linked using bisacrylamide. This chemical cross-link based hydrogel have high mechanical strength due to strong covalent bonds, and it is highly stable and it do not degrade easily in aqueous environment, and the swelling behavior can be fine-tuned by adjusting the degree of cross-linking. We can increase the cross-linking or we can decrease the cross-linking, and this biocompatibility depends on the material used and again it depends on the cross-linker. For example, if you are using glutaraldehyde, it may reduce the biocompatibility, because if you are using high concentration of glutaraldehyde, it may have some toxic effects. And it has a lot of application in the biomedical field, especially in case of drug delivery, because it has a very good swelling and stability. It can be useful for controlled drug release, and also it can be useful for making scaffolds for tissue engineering application. Let us see the next example, that is physical cross-linking. Here the hydrogels are connected through non-covalent interactions such as ionic bonds, hydrogen bonds, van der Waals forces, or hydrophobic interaction. These cross-links are reversible and environmentally sensitive. Some of the examples are alginate. Here we can use the ionic cross-linking with calcium ions, and we can also use this chitosan, where the hydrogen bonding with polyalkylic acid can be used as a kind of physical cross-linking. And third one is PVA, that is polyvinyl alcohol, hydrogen bonding during freeze-thaw cycling. So these are some of the examples of physical cross-linking. Let us see some of the properties of physically cross-linked hydrogels. The first one is mechanical strength, which is generally lower than the chemically cross-linked hydrogels, and stability wise also it is less stable due to reversible bonds, which makes it biodegradable. And swelling behavior, it is highly responsive to external stimuli. And the fourth property is biocompatibility. The biocompatibility is better than the chemically cross-linked hydrogels, because here we are not using any toxic cross-linking agents. And in the application part, we can use this hydrogel for various drug delivery application, especially in case of smart drug delivery system. For example, we can make a pH sensitive or temperature responsive drug release. In case of tumor, we will have a acidic pH. We can make a smart drug release system which is sensitive to acidic pH. We can release the anti-cancer drug and destroy the tumor cells. And we can also use it for wound dressing application, as it has very good biodegradability. It can be very useful for wound dressing application. So what is biodegradability? That means if the particular material is degrading inside this system, it should not induce any adverse effects. The degraded product should not induce any adverse effect. And we can also use this for biosensor application, as it has a very good stimuli responsiveness. We can also use it for biosensing application. Let us see what are the various methods available for hydrogel fabrication. The first one is physical method. Under the physical method, we have freeze-thaw cycle. So we can use the freeze-thaw cycle to create physically cross-linked hydrogel. Example is PVA, that is polyvinyl alcohol. And we can also use the self-assembly. Self-assembly means it is a spontaneous organization of molecules into structured network. Example is peptide-based hydrogels. Next one is the chemical method. In the chemical method, we can go for photo cross-linking. Photo means light. We can use the UV or visible light, and which can induce the polymerization or cross-linking. Example is Gelma hydrogel, that is a gelatin methacrylate. And next one is ionic gelation. Here the polymers like alginate, we can use the divalent cations, and which can cross-link the polymer chains. Example is calcium. And third one is click chemistry, which allows the highly efficient and specific cross-linking reaction at room temperature. And we can also have a emulsion polymerization, where you will be using two immiscible phases like oil or water to create a microgels or nanogels. Let us learn stimuli responsive hydrogels in detail. These stimuli responsive hydrogels undergo changes in their physical or chemical properties, such as swelling or shrinking, in response to specific triggers. It can be pH, or it can be light, or it can be temperature, or electric or magnetic field. Let us see some of the examples with details. The first example is temperature responsive hydrogels. These hydrogels respond to changes in temperature, typically due to the balance between hydrophilic and hydrophobic interaction within the hydrogel. The example is poly N isopropyl acrylamide. So this polymer contains hydrophobic isopropyl groups and hydrophilic amide groups. The temperature fluctuation causes hydrogen bonds changes, which result in swelling or shrinkage. So this can be useful for smart drug delivery system. With respect to the temperature, it can release the drug. The next one is light responsive hydrogels. These hydrogels contain photochromic or photothermal molecules that react to specific wavelength of light. Some of the examples are like polyacrylamide co-spiropyran. The spiropyran moiety undergoes a reversible isomerization between hydrophilic and hydrophobic states under UV or visible light, which leads to the change in the swelling behavior. So the application is we can use the photo controlled drug delivery or tissue engineering. For example, we can use the light, and with respect to the light, we can control the release of drug. So this is a light responsive hydrogel. The next example is electric field responsive hydrogels. These hydrogels respond to electric fields by electrophoretic movement of charged polymer chains leading to swelling or contraction. Example is polyacrylic acid hydrogel. It contains ionizable carboxyl group which dissociate under an electric field, causing electrostatic repulsion and hydrogel expansion. This can be useful for making actuators and biosensors. And fourth one is magnetic responsive hydrogels. Here we will be incorporating the magnetic nanoparticles which allow the hydrogel to respond with respect to the external magnetic field. We can use the alginate and we can use the magnetic nanoparticles. The polymer network is inert, but when you add the magnetic nanoparticle with the help of external magnetic field, we can induce the structural changes. Some of the application is we can have this controlled and targeted drug delivery with the help of external magnetic field, or we can use it for soft robotics. The next one is pH responsive hydrogels. They contain acidic or basic functional groups that ionize or proteinate at specific pH levels, altering the swelling behavior. Example is polyacrylic acid PAA, and this PAA contains carboxyl groups that ionize at higher pH, increasing the electrostatic repulsion and swelling. This can be useful for various drug delivery, including the drug delivery system for gastrointestinal tract for releasing the drugs at specific pH. Let us see how to characterize the hydrogel. The first one is we have to characterize the stretchability of the hydrogel using UTM, that is Universal Testing Machine with a low force load cell. This UTM measures the hydrogel's ability to elongate under tensile force. The hydrogel samples are stretched until it breaks to determine the parameters like elongation and tensile strength of the hydrogel. So this tensile strength is very important for tissue engineering application. How we can adjust these parameters? For example, if you are increasing the polymer concentration, it will reduce the stretchability due to higher crosslink, and we can lower the crosslink density. It increases the stretchability but reduces the strength. The next one is compressibility. We can use the compression testing machine to measure the resistance to compression, which will be useful for load bearing application. For example, if you are fabricating a scaffolds for bone or cartilage repair, this compressibility is one of the important parameter. If you are using the high polymer concentration, it increases the compressive modulus, but it decreases the elasticity. And if you are using the less cross-linking agent, it will lower the compressive strength and stability. Let us see how to study the drug release from the hydrogel. Here we have to keep the drug loaded hydrogel in a buffer solution at 37 degrees Celsius. Then we have to use the UV visible or fluorescent spectrophotometer or HPLC to measure the drug concentration released over time. This drug release kinetics is very important for drug delivery system. If we have a higher cross-link density, slower drug release due to reduced pore size, and if we have a low polymer concentration, fast drug release but poor control. The next one is rheology. The viscosity of hydrogel is evaluated using a cone and plate viscometer or rheometer, because the viscosity is an important parameter for injectable hydrogels. If you are making an injectable hydrogels, the viscosity plays a very important role. The viscosity is directly linked to the extent of cross-linking. So we have to optimize the cross-linking if you are going for a injectable hydrogels. The morphology of hydrogel can be studied using scanning electron microscope or transmission electron microscope, and we can also measure the pore size using the SEM, but for that we have to use the ImageJ software and we can calculate the pore size. And the porosity also can be studied using various methods. The pore size distribution can be studied using mercury intrusion porosimetry, or we can use this BET analysis, which uses physical adsorption and desorption of gases to determine the porosity. The porosity is one of the important parameter for fluid exchange and drug release. Based on the porosity, the drug release can be slow or it can be faster. So that's why the porosity is very important parameter. If we have an increased pore size, it enhances the drug loading, but it weakens the mechanical strength. And if you have a smoother morphology, it may reduce the surface interaction for bio applications. The next one is swelling studies. The swelling study of hydrogels evaluates their ability to absorb fluids. So that's why the swelling study is very important. So we have to use the dried hydrogel sample and we have to rehydrate using the swelling medium, that is water, and we have to measure the weight at various time intervals to study the swelling kinetics. Here this WD is the initial weight of the dried hydrogel and WS is the weight of the hydrogel after swelling. The swelling properties are very important to predict the behavior of hydrogel for various biomedical applications. Let us see some of the applications of hydrogel. The first application is tissue engineering. These hydrogels can act as a scaffold for cell growth and tissue regeneration, and we can also use it for contact lens, as hydrophilic nature ensures the comfort and hydration, and we can also use it for wound dressing. It provides a moist environment and promote the healing and protect the wound, and we can also use it for drug delivery application. As I told earlier, we can use these hydrogels for control and sustained release, and we can also use it for smart drug delivery, and we can also make an injectable hydrogel, which is one of the minimally invasive technique for drug release as well as for regenerative medicine application. And these hydrogels are responsive to external stimuli, so we can use it for biosensor application. Let us see some of the challenges in the hydrogel synthesis and how to overcome those challenges. The first one is stretchability. If you have a brittle gel, reduce cross-link density or polymer concentration. If the hydrogel is weak under compression, increase the polymer concentration or add reinforcing pillars. If the drug release is too fast or too slow, optimize the pore size and cross-linking density. If the morphology is having poor surface structure, adjust the synthesis condition like pH or temperature, and if there is a uneven pore distribution, you can optimize the polymer blending, and if there is a rapid degradation, increase the cross-link density, or you can also add protective additives. I hope you got overall idea about the hydrogel. Let us learn about nanogel. Nanogels are nano-sized hydrogels. So whatever I explained about the hydrogel, those things can be applicable for the nanogel also. These nanogels are smaller in size, between 20 to 200 nanometer, and due to its high surface area to volume ratio, these are the excellent carrier for targeted drug delivery application and biomedical imaging application. Let us see what are the various methods available for nanogel preparation. The first one is emulsion polymerization. Here the monomers are polymerized in a dispersed phase stabilized by surfactants, homogeneous to produce uniform sized nanogels. The next method is ionic gelation. Here we will be using this cross-linking of charged polymers, example alginate nanogels. So this is one of the simple and efficient method for biopolymer based nanogels. The third method is desolvation or nano precipitation. Here the polymer precipitate out as nanogel upon addition of non-solvent, that is the organic phase. The fourth one is the reverse Meissel polymerization. Here the polymerization occurs inside surfactant micelles forming a nanogels, and which requires the surfactant as well as the cross-linkers for making this kind of nanogels. Let us see the difference between hydrogels and nanogels. These nanogels are nano-sized hydrogels, as I told earlier. The size is in the range of 20 to 200 nanometer. As the size is smaller, and it will have a high surface area to volume ratio, enhancing its interaction with biological system, and also due to its small size, it can be very useful for targeted drug delivery. And this nanogels and hydrogels both have wide application in the biomedical field. I hope you understood the basics of hydrogel and nanogel. Let us go to the lab and learn how to synthesize hydrogel and nanogel. In this demonstration, we are going to make guar gum hydrogel cross-linked with borax. For this, we require the following materials: guar gum powder, sodium tetraborate, beaker with a magnetic bead, measuring cylinder, ultra pure water, tissue paper, spatula, microtips, micropipette, and a magnetic stirrer. We are going to make guar gum solution. So first weigh approximately 500 mg of guar gum powder, then measure 50 ml of ultra pure water and add it to a beaker. Keep the beaker on stirring at 400 rpm and 37 degrees Celsius. Add the guar gum powder slowly to the beaker and wait for 1 hour to get a homogeneous solution of guar gum. You can see that a homogeneous solution of guar gum has been prepared. Now we will cross-link it with sodium tetraborate. For this purpose, we have already made a 5% weight by volume solution of borax. Add 250 microliters of this 5% borax solution dropwise to the guar gum solution. You can see that instantly after addition of borax, the gelation process has started. The guar gum solution will continue to gelate for the next 1 hour. A solid gel mass has been formed. We will leave it for 4 hours in a petri dish at room temperature to allow the gel to set properly. After the incubation, the guar gum solution has completely set into a solid gel mass. The gel is also able to hold its own weight. This guar gum hydrogel is a self-healing gel. So if we cut the gel mass into 2 parts and then allow the 2 parts to join together, the 2 parts will join together and again form a single hydrogel mass. You can observe that the 2 parts have joined together and it is also able to hold its weight. So in this lab session, we have made guar gum hydrogel cross-linked with borax. The scanning electron microscopic image of guar gum hydrogel reveals a well-defined porous structure. The porous nature of a hydrogel is important because it facilitates the efficient movement of fluids and molecules within the gel. This makes it ideal for applications such as drug delivery, tissue engineering, and wound dressings, where the ability to absorb and release substances as well as provide space for cell growth and migration is crucial. The size and interconnectedness of pores can be precisely controlled to optimize these functions depending on the specific application. In this experiment, we will learn how to synthesize a nanogel using sodium alginate and Pamam dendrimer. The materials required for this experiment are sodium alginate, EDC, a vial with a magnetic bead, ultra pure water, 25 mg dissolved in 2 ml Pamam dendrimer solution, 10% calcium chloride solution, micropipettes and microtips, and a magnetic stirrer. First, we have weighed and kept 50 mg of sodium alginate, which will be dissolved in 2 ml of ultra pure water. Begin by adding 1 ml of ultra pure water to the vial. After that, add the weighed powder of sodium alginate, followed by another 1 ml of ultra pure water. Now set the temperature to 37 degrees Celsius and the RPM to 700. Let it stir for at least 1 hour to ensure that the sodium alginate completely dissolves. For safety, we are placing cylindrical cardboard around the setup due to the high RPM. After 1 hour, we can see that the sodium alginate has dissolved completely. Now we will switch off the RPM and add 20 mg of weighed EDC to the solution. Once the EDC is added, switch on the RPM and keep it running for 1 hour to activate the carboxyl groups of the sodium alginate. After 1 hour, we will slowly reduce the RPM to 250. Once the RPM is reduced, add 2 ml of Pamam dendrimer to the EDC activated sodium alginate solution drop by drop. You will notice that the viscosity of the solution gradually increases as the Pamam dendrimer cross-links with the alginate chains. If we need drug encapsulated gels, we should add the drug before this step. Now we have added 2 ml of Pamam dendrimer. Close the lid and reduce the RPM to 100. Leave it for 1 hour as an incubation time. After 1 hour, we observe an increase in the viscosity of the solution. Next, carefully add 1 ml of 10% calcium chloride solution to the center of the vial. This is a crucial step, so it must be done with great care. Once the calcium chloride solution is added, switch off the RPM. We can now clearly see that the gel formation has occurred. Leave the solution for overnight incubation. After overnight incubation, the gel has formed, as we can clearly see in the vials. Using a spatula, we will take the gel and put it in this Petri plate. You can wash the gel with ultra pure water and use it for further applications. So in this experiment, we have learned how to synthesize nanogel. So this is a synthesized nanogel. So this can be characterized using FTIR. So this peak in sodium alginate corresponds to OH stretching vibration, and these two peaks corresponds to carboxyl stretching vibration, asymmetric and symmetric of the carboxylate salt groups, and this one corresponds to COC stretching of saccharide structure of alginate. So the next one is alginate gel with calcium chloride cross-linking. Peak at 1630 was intensified, and the symmetric carbonyl peak shifted to higher wave number, that is 1430. So this 1300 and 800 represents the CO stretching and bending, and this one is the alginate gel and formed with the help of PAMM dendrimer. After chemical cross-linking with the EDC and PAMM dendrimer, carbonyl peak at 1630 redshifted to 1640. Also, you can notice the amide linkage bond formation at 1580, and internal CH2 groups of PAMM can be observed at 1450 and 1410. Here you can observe the CN vibration as amide group is introduced in AgG5 structure, and this 720 represents the CH bending vibration. The formation of cross-linked AgG5 nanogels was justified by this FTIR analysis. The mechanical strength of the nanogel or hydrogel can be measured using UTM. Elongation at break has an inverse relationship with the tensile strength. The elongation at break value for AgG5 was far less than the Ag nanogels. So therefore, the chemical cross-linking of alginate with the PAMM dendrimer can significantly alter the mechanical strength of AgG5 nanogels. Although nanogels and hydrogels appear similar, when lyophilized, the dried nanogels can be dispersed in PBS to achieve the desired solution concentration. Then the solution can be analyzed through electron microscopy to assess the size, morphology and structure of the nanogels. As a summary, in today's lecture, we have learned about the basic overview of hydrogel and nanogel. We also learned about the properties of hydrogels and what are the various factors involved in the hydrogel fabrication. We also learned how to characterize the hydrogels, and by practical demonstration, we also learned how to synthesize hydrogel and nanogel. Thank you for your kind attention. I'll see you in another interesting lecture.